Welcome, and in this video I will be discussing about the objects that are moving in a uniform circular motion. So it's a known fact that objects on a rotating disk will tend to stay on top of it depending on how fast the object is rotating or how fast the tangential velocity is. So the tangential velocity is the equivalent straight line velocity of an object that is moving in circle. Now, if it's moving too fast, as we have seen in previous videos or other videos from other sources, that this coin, let's say this is a coin on top of actually it's a coin that is on top of a rotating turntable or disc. Okay, so a problem states that consider a coin of mass m placed on a rotating surface a distance r from the axis of rotation. The surface rotates with a period of t. There are some locations on the surface where the coin can be placed. So you can place the coin here or can place closer to the center of rotational axis. At the locations the coin will slip because static friction, or I missed something, and at the force of static friction, so it's only the static friction. It is static friction, it's not kinetic friction, because if it's kinetic friction then it's going to move. Therefore, just like what happens in some of the observations we made in the past, that the coin will definitely slide or fly off from the surface. So the location should be the correct location. The speed or the rotational speed or tangential velocity should be correct, or the proper speed in order to maintain its place. So therefore, what are some of the things that we need to solve for? So we want to figure out the free body diagram. So what are the different forces acting on the coin? So this is the coin itself. Okay, so let's analyze it from our illustration. This disc is rotating, for example. So this is our rotation. So that's our rotation. And I will use the blue ink right here to represent the tangential velocity. Okay. As we have learned last time, this is the tangential velocity v. So v. Okay, so v or velocity. While the red one is either rotations per second or revolutions per second. Okay. It's rotational speed. Now, using our green ink, our acceleration or centripetal acceleration is going towards the center. Center seeking, centripetal acceleration. Okay, centripetal acceleration. So now, let's draw the forces acting on our coin. Okay. So first, everything on Earth would experience what we call gravitational attraction. So before we draw it on our dot, let's analyze the actual figure, the diagram. So I would have my x and y coordinates. So let's say this is my x and y coordinates. If you notice that the centripetal acceleration is actually along the x-axis of that imaginary x and y coordinates on our coin. So this is our x. Okay. So the first force that is acting on the object would definitely be our force of gravity. Since every object on Earth would have the force of gravity or mass, and that is causing it to be pulled downward as part of our centripetal, as part of matter, where we have mass, and then you multiply it by the gravitational field strength of the planet. In our case, it's the Earth, so that is multiplied by 10. What's opposing that force? It's on a flat surface, and for that case, that's our disk, then that is our normal force. So there should always be normal force and force of gravity. Now there is a pending motion, and that pending motion right here is the coin will slip away. Okay, so the coin will try to slip away. Okay, so we'll try to slip away. So it will slip away on that direction, away from the disc. It's not going to go inward, but it's away from the disc. So what is preventing it? Okay, what is preventing the coin from slipping away? Okay, so I will write it down. This is the pending motion. Pending motion. Okay, or I would say coin wants to move this direction. Wants to move this direction. So it wants to move this direction. So it wants to move this direction. Now, what will happen is that something is preventing it from moving towards this direction. And what is that? It's because of the presence of friction between the surface of the coin and the turntable. And since it's moving towards away, then friction is pulling it or preventing it from going away by applying that force that is towards the center. So it should always be opposite the direction of motion. So this is our force of friction, which is represented by F. Okay. So question is, calculate the centripetal acceleration. Letter B, what is the maximum tangential velocity of the coin? Okay. How fast can it go? Okay. How fast can it go? And what is the coefficient of friction in terms of given variables and constant? Right. So if you want to figure out the mu, which is the coefficient of friction, in our case static friction because it won't allow it to slide, how would you do it? Okay, so how will we do it? So let us move on with step letter B. But before we move on to step letter B, there are some informations that we want to remember. First one is that force of friction is mu multiplied by the normal force. And then our force of gravity is mass multiplied by g. It's either gravitational field strength or acceleration due to gravity. Centripetal acceleration is the velocity, tangential velocity squared over r, radius. And of course, the tangential velocity is simply equivalent to 2 pi multiplied by the radius over the period t. So those are some of the information that we need to remember. Another thing is, in the past, if we have, let's say this dot is not moving in circle, if it's moving in a linear direction, say this is the direction of motion, and you have an initial velocity that is not the same as the final velocity. Okay. So if this is the direction of motion and then suddenly you want to slow down, if it's less than initial velocity, then the acceleration is negative or different direction. So in this case, if it's going on a straight line, we just use A. Okay. But now the difference is for this object that we are trying to determine, okay, is it's moving in circle. So let's say I'm going to use my template over here to just draw a circle that we need. Okay, so let's say this is my template. So using green to represent the direction or the path of its motion. So assuming that it is moving this way, this is top view, this is top view. Okay. So you're looking at it on top, or looking at this one on top of it. Now we have our coin on the right, while in this case, the coin is just moving straight. This time, the coin is moving in circles. And we have learned, and we all know this, that the acceleration is going to the center, as that's why it's called centripetal acceleration or center-seeking acceleration. Tangential velocity is perpendicular to our acceleration. So that's why it's called tangential velocity, because it is outside of the circle and it is in the form of a straight line. Okay. So over here, if we use Newton's law of motion, we will apply the summation of forces is simply equivalent to, or summation of forces of y is equivalent to mass times the acceleration of y, and the summation of forces along x is mass multiplied by the acceleration of x. Most of the time, or almost every solution that we have, if it's on a flat surface, we all make this assumption, or we all know that it's not moving up and down. Okay, so the object is not going up or down, or doesn't change its state of motion. So that's why we all say that the summation of forces, or the net force along the y-axis, is simply equivalent to 0, because the acceleration along the y-axis is 0. While most of the object that is being pushed sideways would have this summation of forces along the x-axis is equivalent to mass multiplied by the acceleration itself. So we are assuming that the acceleration, if there is a change in state of motion, that is our equation, which is Newton's second law of motion, that the net force is equivalent to mass times the acceleration. In our case here, since it's moving in circle, yes, there is what we call y and x-axis. We can simply use the same equation for y, which is summation of forces along y-axis. But in our case, at this point, for this specific problem, there is no, for this problem only, there is no acceleration or change in state of motion along the x-axis, along the y-axis. So therefore, we can say that that is 0. Now, in terms of the x-axis, where we notice right here, we have the summation of forces along the x-axis, okay, is equivalent to our mass, but this time, instead of using the linear acceleration, we will be using the centripetal acceleration to represent this. Now, in our configuration that we used here for linear motion, okay, so as I'm pausing and I'm trying to go back, oh, I realized that if it's going to the left, it's positive. If it's going to the right, if it's going to the left is negative. Sorry, that was my mistake. Okay, so that is negative. Anything going to the right is positive. Left and then right, we have positive, left is negative. Anything going upward is positive, anything going downward is negative. In our case right here, anything going upward, okay, is positive, of course. Anything going to the left is negative, just for this scenario. Just for this scenario, which is called the horizontal plane. Okay, horizontal circle, horizontal circular motion. Okay, there will be another one which is vertical, and the way we analyze it will be different. Summation of forces along x. So you would say, oh, negative to the left, positive to the right. Here in our case, it's different. So we can say it's positive if it's the same direction as same direction. So let me just write it down. So same direction as centripetal acceleration. So if they're going to the same direction, just like here, centripetal acceleration is going to the left, and that is the same direction as force of friction. So not because friction is going to the left means it's negative, because that's for linear. Instead, it will be positive because it's the same direction as your centripetal acceleration. Now, let us move on. Now, we can solve for letter B. So, for letter B, calculate the centripetal acceleration of the coin. So, why don't we start by analyzing the forces? Summation of forces along y equals 0. And what are the different forces acting on it? We have positive Fn minus Fg, which is going downward, is equal to 0. Now, Fn can be equal to Fg, because if you move this to the other side of the equation, okay, so you add Fg on both sides of the equation to cancel, so therefore you have positive Fg. And we all know that Fg is simply m times g. So we can say that this is Fn is simply m multiplied by g. That is for summation of forces along the y-axis. How about summation of forces along the x-axis? So the summation of forces along x-axis is equivalent to mass times the centripetal acceleration. This is only true, okay, if we are solving horizontal uniform circular motion. So what are the different forces? We have F, or force of friction, is equivalent to mass times AC. Now, force of friction, is it positive or negative? Definitely, if you're talking about linear motion, you would say it's negative because it's going to the left. But since the centripetal acceleration is the same direction as our force of friction, so therefore we can say that this is positive. Now, how do you solve for the centripetal acceleration? All we have to do is divide both sides by m to cancel out m on one side of the equation. So therefore we have centripetal acceleration is simply equivalent to the force of friction divided by m. Force of friction divided by m. But we all know that force of friction is mu, since we are given the value of mu. And force of friction is simply mu times Fn, which is our normal force, divided by m. Going further, mu Fn is simply equivalent to mg divided by m, which cancels out our mass. So therefore, our centripetal acceleration is just simply equivalent to the coefficient of friction multiplied by the acceleration due to gravity. Now for letter C. Okay, so for letter C, a lot of you might be tempted of just using the equation, which is 2 pi r over t. Okay, 2 pi r over t. That is the equation. If you know the t, you know the r, you know the 2. Of course, pi. Now, question here is, what is the maximum tangential velocity of the coin? Okay, so at any given point in time, okay, what is the maximum velocity? So it means we need to derive an equation. So why don't we use this relationship of centripetal acceleration? Centripetal acceleration is equivalent to the square of the velocity over r. Cross multiplying, so now we have a of c is equivalent times r is equivalent to the square of velocity. Okay, square of velocity. Now, we know that a of c is simply equivalent to the mu of g. So we can just substitute the value of ac from the ac that we solved from letter B. I know I said before, do not use value from previous steps because you might make a mistake on the previous solution, and then your following solution might be incorrect also. However, it might be good to use it just because if you are sure of your answer, you can definitely use it. So we can say that velocity is simply equivalent to the square root of AC and R, and then plug in the value of AC, which is mu G times R, and just take the square root. So that will be the maximum velocity. So that will be the maximum velocity. So that will be the maximum velocity. Okay. Now, since we are trying to solve for the coefficient of friction, so let's solve for letter D. I want to solve for the coefficient of friction. Okay. I want to solve for the coefficient of friction according to the problem. And that is to take this equation right here, which means the summation of forces along the x-axis is equivalent to mass times the centripetal acceleration. At this point, we can use this equivalent centripetal acceleration because it's actually moving. This one is actually moving at a certain velocity. Now we can say that this one is your force of friction equivalent to mass times the centripetal acceleration. But the centripetal acceleration, A of c, is simply equivalent to the square of the velocity divided by t. But since velocity is also 2 pi r over t, now we can plug in the value of saying that the force of friction is equivalent to mass times the square of the velocity. So this one is divided by r. So this is 2 pi r over t, and then you have to square the whole thing. So let me just change this parenthesis into a bracket. So let's use the parentheses for the inside variables. This is your square, and the whole thing is in your parentheses or bracket. Just move this right here. And we also know that force of friction is mu times Fn. Mu times Fn, which is right here. But Fn is also mg, as we use it here in the previous solution. So we can change our force of friction, which is mu, or coefficient of friction, multiplied by m and g, is equivalent to m. And that will give us 2 times 2, that is 4. Pi times pi is pi squared. R squared over t squared divided by r. Then close your bracket. Oh, I can cancel my radius, one of the radius. I can also cancel my mass if I divide mass on both sides of the equation. Now I have mu times g is equivalent to 4 pi squared r over t squared, and then our mu for this given problem is simply 4 pi squared r over g and t squared. So this will be our answer to question letter D. Okay. Hope it will help you to solve similar problems in the future.